me put it on recording. So we'll recall how we find all these special types of numbers, and I think the good idea will be to actually see what we had for a quiz last week. There was a little problem related to the finding of those different kinds of numbers based on the exercise. Which one was it? Was it number 2? Remember which problem we had for the quiz last time? I think there was one of these sets of numbers, 1 through 4, and I asked for finding integers or something. Please remind me if that's right. Did I ask you to do exercise number 2, part E? Oh, no, not E. C, the integers. Is that right? We had a little quiz. Just want to make sure I do exact same problem that is in the, oh, great that you remember. Thank you. So integer numbers. So let's first of all see what the integers are. Integers. They called with that capital Z sometimes. It's a big Z. So we have the whole numbers such as 0, 1, 2, etc. And also their opposites such as -1, -2, -3, etc. in the other direction. So those are integers they talking about. And turns out in this set we have -7 that works, 0 that works, and the square root of 49 that also works, because square root of 49 is actually 7, right? Although they wrote it with a square root, but you can extract that square root and this be number 7. And that's fine, that is one of the integers. So I just underlined 3 numbers that are called integers. And 2 not underlined numbers, well, they're not integers, right? So integers is very popular type of question that you see in lots of math classes. I guess those are the most interesting ones. If you would like to do something with the irrational numbers, like here, part E is irrational numbers, then the only irrational number will be a square root of 50 in this exercise number 2, because the rest will be integers, and 0.6 with a bar is actually 0.666 dot dot dot. So that's actually the same as 2 over 3. That's a fraction. So it turns out that irrational numbers are the ones that we see with the square roots or number pi. Number pi is also irrational. But square root 49 is not irrational because this is really 7, so it's not a square root. They just wrote it with a square root, but it's just 7. And that's good to realize. So irrational numbers, the square roots, those are a little bit unusual, right? And of course, all of these numbers, we had a name for, they're all real numbers or reals. And real numbers will be all of them. All. In fact, the real numbers is also always going to be the answer for every one of these exercises. So they're all real numbers. It's always deal with real numbers. There are no other numbers that we encounter on number line. So last time we started to talk a little bit about this section, and I guess I can do some more problems here in this section, such as, for example, recall so-called distributive property of numbers. And you probably already know what that means, right? That's how we get rid of the parentheses. We distribute. So I multiply 5 by 6 and I get 30 here, 30. And then I also multiply 5 by a square root of 2, so it'll be plus 5 times square root of 2. So to distribute means we just multiply the number outside the parentheses by whatever's inside, like that. Distributive property. Okay, so, well, there are various properties that people utilize to deal with numbers. And in the rest of section, they actually mention some of those, such as associative property. Let me say a few words about those. Associative property of numbers. And turns out the associative property works with addition and subtraction. So people usually say if you have A plus B plus C, then it doesn't really matter on which way you add those three numbers. So you can put parentheses around the first two or parentheses around the last two. So you can start with the last two, add them, and then add first, or vice versa. And that's exactly what we have in here. So if you have associative property, then the same 3 and then 9 will be right there. In other words, you had parentheses around the first two, now you have parentheses around the last two. Turns out the associative property also works with multiplying numbers. So if you multiply 3 numbers, A, B, and C, then you can multiply first two, or you can start with multiplying the last two, and the result is going to be the same. Please notice that other operations such as subtraction and division not going to work with this associative property. So if you want to look at exercise 17, then to fill the rest, so it's 4, 5, and 3, we put right there. And we see that it doesn't matter, you multiply 4 and 5, so it'll be 20 times 3, 60. Or if you go 5 times 3, which is 15 times 4, you also get same result, number 60. So just to be aware that there are such properties present. Well, it turns out there is another property they're talking about here called commutative. Commutative property. And it also works with two operations such as addition and multiplication. So if you add the numbers A with B, then you can actually start with B and add it with A. So it doesn't really matter on what order you add numbers. And the same thing we use when multiply. So no, it doesn't matter how we multiply in what order. In fact, if you remember when you learned timetable, you probably memorized that if you know how to multiply 6 by 8, then 8 by 6 will give you exact same answer. So multiplication makes no difference in which order. So to illustrate this with example, I can take a look at problem 13 that says 4 plus 5 is exactly the same as 5 plus 4. So we don't really have to add anything. We just see that the order of addition doesn't really matter. And that's exactly where it appears. So 4 plus 5 or 5 plus 4 give you exact same results. And analogously with multiplication, notice that if you multiply square root 5 by 4 or 4 times square root 5, if you flip these two numbers, people say if you commute those two numbers around the minus sign, well, the result is still going to be the same, so it will make no difference for us at all. And that's great to realize. So we have these little properties here. Well, so there are various distributing and other procedures that appear in the next group of exercises. So for example, if I look at 34, and I notice that the order of these three numbers is the same, right? But all I did, I moved parentheses from the end to the front. So it looks like moving parentheses when we deal with three numbers will have associative property of multiplication, right? Property of multiplication, which is being used. So you multiply them, but you move parentheses around. So that's what they want. So these exercises that may not seem to be standard because you don't have to calculate anything. What you need is to state the name of the property illustrated. So what property this is? What property did we use? Well, it turns out it's associative property of multiplication. You say, Alex, why do we need all that? We used to just take numbers and multiply and get the answer. So why did you talk about some kind of properties? Well, these properties is what we take for granted when we do calculations. And in this section, they trying to explain why. So they give us reasons why we actually do these things. So there are some special rules, or in math, they call properties that being utilized. And that's the reason why they want. Like, for example, problem 29 looks like they commute two numbers, so that'd be commutative, right? Property of addition, commutative property of addition. Notice when you add, you put addition. When you multiply, you say it's a property of multiplication. And none of these exercises have subtraction or divisions. Notice that properties are only work for addition or multiplications. And say, but what about this one? It looks like you have the exercise 35, where you do have some negative numbers. Well, you actually distribute here, right? Notice it's called distributive property. So numbers, yes, could be negative, but it's not subtraction. We have multiplication here. So it's a distributive property is what we're using. We distribute to get minus 16 and then plus 12. When you say this is -4, yes, it is, but they don't ask to calculate. They ask what property is shown here, and we distribute. That's another property that we utilize. So this chapter, I think, is nicely going, and I can check out the next. So I guess you don't have to continue with this next page. So just as usual, try to have you do only problems on the first page of that section. So I'm not trying to get real deeply into all that, just to show you properties. So you can just do exercises up to 35 on this page. You can do a print screen of it, or it should be in the recording. I hope it'll go through, but just in case, it's a good idea to do a print screen of this right now. And I'm gonna move to the next section. So section 5.6, that is another very popular story that talks about scientific notation. That's very important section because very often we need to use a calculator, and a calculator gives us numbers that sometimes don't look the way we expect them to. And that means the numbers are given in so-called scientific notation. Let me show you how this looks like. For example, here exercise about scientific notation, it says 4.5 times 10 to the power of 9, right? So what does that mean? 10 to the power of 9. Well, it means there should be 9 zeros here, right? So it's really 4.5 multiplied by 10 times 10 times 10. So there'd be actually 9 zeros in this number, because that's 9's power of 10. And when I do this multiplication, what people do is move the decimal point 9 places to the right. So they move it once, they get 45, right? And then they keep moving it again and again, and they're actually attaching 8 zeros to the number. So we end up with some kind of huge result, right? Like 4 billion. Actually, we're multiplying it by billions. So it's a 4,500,000,000 and no thousands, which is there's 4 billion. And the calculator gives the answers in that form. It's called scientific notation. Usually because the number is way too long to fit into the calculator screen. And sometimes when number is also too long, but being very, very little, like the one we have here, is also coming out as a number in scientific notation. So what does this mean? 1.1 times 10 to the power of -4. Well, we're gonna have to move your decimal point, but now not to the right when we multiply it by 10 to the positive power, but to the left because of negative power, right? So I'm gonna have to move it once and then 3 more places. So it'll be 3 zeros here in front of 11. So this is a microscopic number, very, very small. And they talking here about the length of wires. So wires is a very, very small, they say. So it's going to be 0.00, so a bunch of zeros in front. So the actual number is what I just wrote here. It's actually called 11 tens, hundreds, thousands, 10,000s, 100,000s. But the way calculator will treat it will be 1.1 times 10 to the power of -4. Well, that's how calculators are constructed, and that's what we should realize. Scientific notation. So it's a special way to write numbers using those powers of 10. Well, and here in this section, they also work with this various exponents. Notice there's some negative powers, positive powers. So there are various so-called properties of exponents that being utilized. So let us take a look at some of these properties. I'm sure you saw them when you took the algebra class, but just to refresh your memories why they work. Turns out the key property is here. So very popular property. So if you divide the power of m by power of n, then what you do is you actually minus those powers, m and n. Did you ever see this property before? So turns out this property is very popular, and here they're trying to explain why 0 power is equal to 1. Notice what they do is they say, okay, so if I divide 4 to the third by 4 to the third, they actually cancel, right? We divide the same thing by the same thing, 64 by 64, and you get 1. But at the same time, I could use this property above. So I will say it's 4 raised to the power of 3 minus another 3. Because this power is 3 and 3 supposed to be subtracted. And this is nothing else but 4 raised to the power of 0. So 0 power is equal to 1. That's very unusual property, one can say, right? Why does 0 power be equal to 1? Well, simply it comes out from that popular property of division of 2 exponents. Division of 2 exponents. There is another popular property that talks about the negative powers, such as negative n, which is the same as 1 divided by b raised to the power of positive n. And one can wonder why this is also working by, well, let's say, take a look at the b, but instead of raised to the power of n, I can put it as 0 minus n. Please notice that still is equal to n, right? Because that 0 really means nothing. It's still negative n. But once again, using this property in the upper left corner, I can write this as a b to the power of 0 divided by b to the power of n, right? And then I'm going to use the fact we just considered. So instead of b to the power of 0, I can put 1 on the top and have b power of n on the bottom. So notice I started with negative power and I ended up flipping it. I brought that b to the power of n down to denominator. And if one wonders why we need such a manipulation, well, the answer is going to be we don't want to see any negative powers. Our powers should not be negative. Negative is no good. We can bring them down to denominators and write them as positive powers. And that's the point of this story. So I think we can take a look at some exercises at the end of the section just for practice, as usual. I think that's pretty much all theory we need here. So let's see. We usually start with doing some exercises and practice, right? So that's what we care about. So let me do some here. Like, for example, start with exercise number 10. Clean a little bit. So I'm sure these problems will make lots of people happy because these problems will be very familiar, because you already saw, I'm sure, how to work with, let's say, powers of 6. You subtract 7 and 5, and you get 6 squared that you can calculate. It is equal to 36. So there are various little exercises in here that you can enjoy. And if I try exercise 5, for example, what power of 2 is going to be here? Wouldn't that be 6? When I say, why is that 6? Why not 5? Well, because 2 squared times 2 squared times another 2 squared is nothing but cube, right? We have this power of 3 on the outside of 2 squared. So when I multiply these 3 exact same powers, I add 2 and 2 and 2, and I get 6. So 2 power of 6. Usually those big powers we don't calculate. We calculate squares, but not 6 powers or bigger powers. So next page continues with more exercises that deal with exponents. So let me clean a little bit of these properties. So this page here. And do some problems on this page. Looks like up to practice plus, we have a whole bunch of exercises in here. So let me clear this out. Let's try something with a scientific notation. Please notice that you have a calculator that you could use, right? Because, for example, doing problem like 102 without a calculator is probably not going to really make much sense, right, to do. So if you want to divide these numbers, so what are they actually? How many decimals? 1, 2, 3, 4, 5, 6, 7. So you can see that this is definitely not convenient to have such number as 7 zeros, right? 1, 2, 3. It's kind of hard to see, and probably that's the main reason why one should appreciate having scientific notation, so you can actually see better how many zeros you have in front, divided by 16,000. I say, Alex, you just copied this. Yeah, I copied so I can enter this in the calculator. Let me do that. Where's my calculator? Here. So I'm going to be taking the point. Now I put 1, 2, 3, 4, 5, 6, 7 zeros and 96. And divide this by 16,000. And look at what I have. 6 times 10 raised to the power of -12. So yes, calculator gives us scientific notation. And if you want to write it as a standard form of a number with all these zeros, then since power is 12, right? Oh, sorry, it's -12. So I have to be a little bit more careful. Better erase this. I need to move my decimal to the left, right? So where do I move it? Well, I have to imagine the decimal point that is not present here. It should sit here after 6, right? Because it's same as 6.0. And then when I start moving it to the left, I go once, and then 11 more places because total is 12. So I actually have to put 11 zeros in front of my 6. So here 6 zeros. I put 5 more, right? So this is a very, very small number. In fact, what's the name of this number? Well, it's a 6, and that's thousands, millions, billions, right? 6 billions is what we have here. So you can go back to the textbook and see what they wanted. And they say, write number in scientific notation. Well, actually, the calculator gave it to me in scientific notation. So it's 6 times 10 power of -2. So it's not very hard. I'm sure you saw these things before. And that's pretty much, I guess, all we care about here. How about some of the power exercises? Let's say, how about exercise number 16 that says 9 raised to the power of 0. And turns out it's going to be 1 because any number raised to the power of 0 is equal to 1. Right? So that's good to realize. We say, okay, what about 20? Well, when I do number 20, maybe I'll do it here separately. I better write this as a 1 divided by 3 squared. Again, the reason is I'm using that negative e to the power of -n, so that negative power property, the way we turn negative powers to positives, right? So I bring this 3 down to denominator and have 1 over 3 squared, which is equal to 1 over 9. And that's the answer. So we can use these properties to work with various negative exponents, like let's say exercise number 28, that I can write as 2 divided by 2 to the power of 3. So analogously, bring this negative third power down to denominator. And then what? Well, then I can simplify this, right? Because I actually, let me continue it here. I actually have 2 on the top and 3 factors of 2 on the bottom, right? And that allows me to cancel the powers and get the answer, which is going to be 4 on the bottom. What's on the top? Number 1. The reason it's 1, because you can factor 2 with 2 times 1. In other words, when everything cancels, it means that only number 1 remains, right? So we get a nice little answer. So the key part here is not to hurry. So if you start hurrying, you start making mistakes. So just write it all down and don't skip any steps and everything will be just fine. Let me do one more, number 37. Look at this exercise. It has lots of different numbers and powers. Well, I notice I can cancel this 3 and 5. 3 and 15 get 5 on the bottom. So I'm going to have 2 in my numerator and 5 in my denominator. And then what? Well, looks like all powers of x are also going to cancel, right? Because here I have 5 and 1 more, so that's x power of 6 on the top. And we still have x power of 6 on the bottom. So I'm going to be canceling these 6 powers of x and get the answer, which is 2 over 5. like that. So I guess this is a section that I'm sure you are familiar with. So you could do a few problems from this page, and I'm sure you're going to like them. So just a refresher of, I'm sure, what you have already seen before. Well, I'm going to be moving to the next section today. I'm going to take a look at something a little bit more exciting. And a little bit more exciting will be, let me clear all that first. Stop share this again. More exciting, we'll deal with so-called sequences. So it's the next section, that's where I'm going to. So these will skip the exercises that are we usually skip. So here they looking at one very interesting infinite so-called sequence, which is produced after one Italian mathematician named Fibonacci. So what he did, he took number 1 and 1, added them and produced 2. So he started with 1 and 1, and then he added 1 and 1 and produced 2. Then he added 1 and 2 and produced 3. So what he was doing, basically taking two numbers and then adding them and producing the next one, 3. So once he ended with 3, then he added 2 with 3. You see what he's doing? And he produced 5. So he would always add 2 previous numbers and produce the next, produce the next, produce the next, and so forth. So if you add 3 with 5, you get 8. When you add 5 and 8, you get 13. You see how it's produced? 8 and 13 is 21. 13 and 21 is 34. So you can do this forever. And that's what they're saying by placing dot, dot, dot. So this is so-called Fibonacci's sequence. Well, that's interesting how he became famous, just took a couple of ones and added them and just kept adding. Well, not because of that, of course, there were other things that he was doing, but it turns out that this type of sequence, people notice in various plants, like here they have a number of seeds that start in the beginning with 1 and 1, and then more and more and more, so they could be described using Fibonacci's sequence, which is quite amazing, right? So in nature, there are lots of examples of such a adding of 2 previous and producing the next. For some reason, we don't know why, it just happened to be, and from observations, just observing these various, I guess, plants, we see those things happen. Well, here's another sequence they have. And this sequence appears, looks like on spending on pets in United States. So it looks like people keep on spending more and more on their pets every year. And that's what they noticed, that in billions of dollars, year 2001, there were 29 billion, and then next year, 31 billion. And then 33, and then 35, and so forth. So every year, the spending increased by $2 billion. How about that? So the pets are getting more and more expensive, I guess, right? So notice every year you add another 2 billion. So that's probably a good business, right? To have some pet-related industry. So if you add another 2, it'll be a next, and then so forth. Next is another 2. So you just keep adding the 2. And that's what produces so-called arithmetic sequence. So you just keep adding exact same number again and again and again and again, and you produce more and more and more terms. So you can nicely describe this infinite sequence just by telling what is your first number is where you start, 29, right? And then you also tell how much you add to. And that's how you can produce all of these terms of the sequence. And that's exactly what they're talking about here down below. So they say the difference in between terms here is 2. And the first term is 29. So if you know these two pieces of data, well, then you can produce pretty much any term of the sequence. So you just say, 29, next term will be plus 2. So you add 2 and you get 31. Then you add another 2, right? And you move to the next term, 33. So it's, I think, a very interesting observation here. We make that you just need to know two numbers, the difference, the gap in between the terms, and the actual starting place, which is called the first term, which is, I can call it A. And that's it. So they look at various examples of these sequences, and notice if I look at the second example, they have, you can see that gap in between terms will be 3, and that's what they actually came up with, 3, right? Because if you add 3, you get 1 and 3 is 4, 4 and 3 is 7. Notice if you start with -5, you add 3, you get -2, and then another 3, you get 1. So yes, the difference is 3. First term is -5. So you can always discover the difference if you have arithmetic sequence, and definitely enjoy the exercise. Like in example 1, it seems that we have another arithmetic sequence here, but we need to add 4, right? So if you add 4 to 6, you will get 10. And then you add 4 once again, you get 14, you see? So the difference is 4. And that's what they're talking about. So they say first term is 6, difference is 4. So you start with 6 and you add 4, add 4, add 4, and so forth. And that's how you produce 6 terms. So they want 6 terms. Okay, so you just add 4 6 times and you get the answer. It's interesting, right? Of course, you cannot produce the entire sequence because it's infinite. You just keep adding 4 and you'll do this forever. And there'll still be more and more and more numbers that you can still produce. So we don't try to get all of them. We just put dot, dot, dot. So they actually came up with a little formula for so-called general term for the sequence. So what does that mean? Well, let me take a look at the example that we just saw before, like example was 29, 31, 33. So we just keep adding and adding, right? And adding. So first term is A, which is here, 29, A1. They say first term, so they put 1. So how they produce the second term, A2? Well, they take A1 and added difference, right? And the difference was 2. So difference is 2. So this is our sequence. Dot, dot, dot. So difference is 2. So they added 2. That's how they move to next, right? How they produce the next one, third term? Well, they again take A1 and they add difference once again. So I can say the difference of 2 is added twice, right? Because you added once and then once again. So people say that's first term plus 2 times the difference, right? So that's for A3. So it's 2, that's 3, right? What about A4? So this is my A3, that's third term. What about fourth term, A4? Well, you again take A1, but you add difference 1, 2, and then 1 more time. So it'll be 3 times difference. So what they do is they try to produce a little formula, and they notice that if you have so-called nth term, then you take A1 and you add this difference, but not times n, but times n minus 1. Please notice that here you had 4, but difference was 3 times, 1 less. Here you had 3, but difference was 2 times, 1 less. So here you have n, difference will be 1 less, n minus 1 times. And that's how they come up with the formula for so-called nth term of the arithmetic sequence. So I think it's convenient because, for example, if they say, okay, what's term number 100 for this sequence? So you're going to have to add 200 times. Well, that's going to take a while, but if you already know your first term, which is 29, and if you need term number 100, then you can get 100 minus 1 times difference, which is 2, and you will get right away the number. So that's like 99, right? So we'll add, let me put it in the calculator so I don't have to make any mistakes. So we'll get this 29, right? Oh, 29 plus 99 multiplied by 2. And you can get term number 100 right away, 227. So you don't have to do this calculation 100 times, right? So you just use this formula and it does it much faster. I say, well, I could still do it 100 times. Well, what somebody asks you millionth term, you're going to do it a million times? Of course not, right? So that's going to take forever, probably a few years. So it's no good. But with formula, it's going to take you same as long as it just took me to calculate 100th term. You just put in a calculator, you'll get some number. So point of story is that formulas are helpful and good. And all you need is just to plug numbers in the formulas and you will always get the answer. And I guess that's the whole point of this story. So let me do some exercises here. I just want to start the section. So I'm going to just look at first group of exercises today. I'm not going to continue. Next time we'll continue because I know it's might a little bit too much for today. So let me just leave this formula for the nth term here and try to take a look at some problems here on the first group of exercises in this section. This is actually going to be last section of chapter 5. So we'll keep working on it this week and then we'll move to next chapter. So let me try one exercise, like say exercise number 3 here that says exercise 3 that says here's the first term, here's the difference, and they say write first 6 terms of the sequence. So I already know how to do this, right? So I put 200. The next term will be 200 plus 20 because difference is 20. So it'll be 220. Next term will be 220 plus again 20. So I just keep adding 20. So it'll be 240, right? That's already 3 terms and so forth. So 240 plus another 20 is 260. And a couple of more, 260 plus 20 is 280, right? 280. So I keep adding that same number 20. And on 280 finally plus 20, I get 300. Of course, the sequence continues forever, but they asked us for first 6 terms, so we gave them this 6 terms, and that's it. Okay, when you say, Alex, what about one with fractions, like exercise number 15? Well, that'd be the same thing, actually. So what you need is to definitely use calculator for this. So an exercise number 15, because otherwise you'll be stuck with these fractions for a while. So 3/2 plus a quarter. So first term is 3/2, right? Next term will be 3/2 plus a quarter. Next term, you'll add quarter, but the question is to what? Well, let me put this in a calculator and you will see 3/2 plus a quarter. Yeah, you could do it by hand, of course, if you feel like it, but I would say just use a calculator. It'll be 3/2, not 3/4. Should be careful. 3/2 plus a quarter plus 1/4, right? So here's your answer, 175. Okay. You can write this as decimal. So next will be 175 plus a quarter. Well, I can do this without a calculator now because a quarter is 0.25, so that's 2, right? Then 2 plus a quarter. Well, that'd be 2 1/4, right? I say, oh, I got the idea. So you just keep adding quarters. So next will be 2.5. Next will be 275. So I don't even have to write all that, right? And I already have my 6 terms here. And the first I can say 1.5. So it looks like all these terms definitely much better to write with decimals rather than fractions. So you can see it's 0.25. You keep adding and get the result. But see, calculator was helpful for us to get to start, to get the idea of how we start. So how about if you do a little quiz exercise, like problem number 2 for quiz for today, write 6 terms of the sequence. And as usual, please send it to me in private and chat. And that'd be our quiz for today.